Hey, welcome to the last session of the day. So there will be 3 talks in this session, mainly focusing on the masking of symmetric ciphers and their low latency implementations. So the first talk is time sharing, a novel approach to low latency masking. The authors are Dilip Kumar, Simon Doge, Joseph Balas, Benedict Gierlix, Ingrid Varvade. So Benedict will give the talk.
Thanks very much for the introduction. So indeed, this is a joint work with Dilip, Zeman, Josep, and Ingrid. The main part of the work is definitely actually Dilip's work, and so it's a bit unfortunate that he cannot be here today. And present the work himself. I'll try to step in and do my best to do it for him. So we've already had several sessions and talks and best paper talks about all the masking topics, so that's good for me because I can skip a lot of why and how and so on stuff and go more or less directly to the meat. So we speak about masking, we speak about hardware, and one approach in masking hardware is what people call gate level masking, in which you basically, you take your circuit, you reduce the representation of the circuit to a composition of AND gates and XOR gates, and then masking that circuit comes down to replacing AND gates with masked AND gates and replacing XOR gates with masked XOR gates, and then in theory you're done. So we have already heard that all the linear stuff, that's kind of easy, so we're not going to look at that, and we mainly, the interesting stuff is always the question how to implement this masked AND gates and so on. So let's look at an example. So if we want to have a masked AND gate, so we want to securely compute the product of 2 bits, and we have these bits given as 2 input shares. So we have the 4 shares that go in the masked AND gate. I don't have a pointer, so I'm going to wiggle around with my hand, and you probably guess where I'm pointing. And so the output should be the shared representation of the AND of the 2 input bits. Okay, so one possible way to do this, we've also heard this already before today, is to use domain-oriented masking, which works as shown on the right side of the slide, where you compute some partial products, you re-randomize them, you have to register them in order to prevent glitch propagation, and then afterwards you can compress and output the shares as you want them. So the important point on that slide is basically the fact that you need this register layer for glitch propagation, which is now here indicated by the red line. So this introduces latency, right? So we need one clock cycle in the middle of this AND gate, so there are 2 compute phases. This introduces latency. And, well, that becomes a problem, of course, if you actually zoom out now a little bit and don't just look at one AND gate, but look, okay, I want to implement some interesting circuit. For instance, an ASS box, if you implement it with a Boyer-Peralta architecture, you'll have at least a multiplicative depth of 4. Yeah, so computing an S-box would then, computing a masked S-box would then necessarily require at least 4 clock cycles. And that can be a problem in certain applications where low latency is, let's say, your highest requirement, where you are willing to pay more area or whatever. But you simply can't, because you would, like, if you would remove any of these registers, you lose your security. Okay, and so so designing efficient, low latency masked circuits turns out to be difficult. Where do I have to point this? Okay, so there are of course some existing works dating back roughly 10 years. So there's LMDPL, which is kind of efficient in area. An area is kind of efficient also in the usage of randomness. It requires to use dual rail pre-charge logic, which comes with some constraints that it needs a pre-charge phase and an evaluation phase and so on. One other thing at least to say about LMTBPL is that There was some claim for provable security, which was later disproven and which is going to kind of be fixed at this conference at some point. But so at the time of us writing the paper, it was kind of, let's say, unclear what exactly is the situation there. We have GLM, which is basically a variant of domain-oriented masking, where you just omit the compression step and your circuit keeps on growing exponential, and then at some point it becomes very large. But it is low latency. And there's a third approach that is GHPC, which uses Shannon decomposition of circuits, and that also turns out to be, let's say, area and randomness hungry. So with that, let's move forward and look at our technique. So what I'm going to present is a novel masking technique with latency 1 cycle. So that's the new thing, irrespective of the algebraic degree of the function that we want to mask. Right? So if you think back a couple of slides, I showed you that for the S-box, the latency depends on the multiplicative depth of the circuit. That's not the case here. Okay? So we always have latency 1 cycle, regardless of the function. And we have that the resulting circuits are provable first-order glitch extended Piney secure. So, and the main idea is illustrated on the slide. So the image on the right is a simplified version. Okay, so this is not the real thing. This is the concept. And the concept simply is, and that's why we chose the title, time sharing, that we separate the processing of the 2 shares of the masking in time, separated by a register in the middle. So in the first phase, we compute everything that we can compute that is only based on share 0 terms. And in the second phase, we compute everything based on share 1 terms. And afterwards, we use these pre-computed, let's say, partial results to actually assemble the final result that, that is desired. So let's look at an AND gate as an example. It's a toy example. Okay, it doesn't make a lot of sense. I will tell you afterwards, but it's an easy example to look at. So this is kind of what we would like to compute. Okay, so we want to compute all the products of the share 0 terms in the first phase, and we want to compute all the products of the share 1 terms in another phase, and then somehow we want to assemble these things together to compute the result we're actually looking for. So we can do it this way because this would be highly insecure. So one of the things we have to do, first of all, is we have to introduce some randomness. Yeah, so we have to remask things, introduce the randomness like this. That's not enough because there could be glitches. So also here we need a register layer to prevent glitch propagation. And for composability, we have this R3 and R4 that we bring in at the beginning. This is what we need to achieve Piney. Okay, so this is basically the full picture, and this is now a functionally correct picture. So we're remasking the inputs. We compute everything that we can compute based on only on terms of the share 0 domain. We remask, we register, and in the second phase, we compute everything that we can compute based on share domain 1 terms. And afterwards, we take all these little things that we have computed now and reassemble them in order to get the output that we wanted to compute. So, and I said in the beginning, this doesn't make sense to do it with an AND gate, and indeed it doesn't, because if you count, like this thing is as slow as an AND gate in domain-oriented masking, and it needs 5 random bits instead of 1. So you wouldn't want to do it, but this is only the concept, right? And so the main idea of this masking scheme is basically that you can now do exactly the same thing, but with any arbitrary function. Yeah, the image that you draw basically looks always the same. So we did it with a Prince S-box in the paper. Prince S-box is a 4-to-4 mapping. So we have 4 input bits. We're computing 4 coordinate functions for the output. The functions are given here on the slide. And so basically, if we want to mask this now with the time-sharing masking scheme, we're doing exactly what I just explained. So in the first phase, we're computing all the partial products that we need and that we can compute using only the share 0 domain terms, and we remask them, and we register them. And in the second phase, we compute all the needed products of the share domain 1 terms, and afterwards, yeah, we kind of multiply and XOR terms together to get the result that we actually need. So, before I show the implementation results, I want to already highlight some advantages. So one advantage is that we can actually reuse some of the terms that we are computed. And I'm showing this here in the non-masked representation because otherwise the slide is just full of notation and that you get lost. But so, for example, if we want to compute the DC term, we are computing those products here on, highlighted on the right-hand side. For the CB term, we have to compute those. And for the DCB term, we have to compute those. Basically showing you, okay, for computing DCB, yeah, I'm already computing also all those other terms that I need for DC and for BC, and I don't have to do this twice. Yeah, so in many other masking schemes, you actually have to compute all these terms again and again, and we just compute them once, and then afterwards pick what we need and plug it where it has to go. And the second thing, what we're doing is that we can also do this reusing across the 4 different coordinate functions. So for example, you see here in each coordinate function, no, in 3 coordinate functions, the term DCB occurs. Yeah? And so we're not computing this 3 times, we're computing this only once. And then we're taking that piece for the first equation, and for the second equation, and for the fourth equation. Another advantage is that with this approach, it becomes very easy to use optimization of EDA tools to make your circuit smaller. Okay, so this is normally, yeah, let's say a two-sided sword, right? So if you allow your tools to optimize your code, you have to be very careful because tools are not security aware and they're going to like take out things or add things that make your circuit insecure. So you have to define a lot of modules and tell the tools what they can touch and what they cannot touch, and so on. In this approach, it is a lot simpler because you can basically allow any form of optimization except register retiming. Okay, and register retiming is the name for you allowing the tool to move combinational logic across the register barrier. Yeah, so if you have like a circuit that is very imbalanced and you have a lot of logic and the register and some little amount of logic, the tools may decide to put some of that logic on the other side of the register to make it more balanced. This is the only thing that's not allowed here. So whatever is before the register layer has to stay before the register layer, and what is after the register layer has to stay after the register layer. So now we go back to implementation results of the Prince-S box. You see here the table showing area numbers, the number of random bits required, and the number of clock cycles for the latency. For our work, you see 2 numbers with the A and with the B. You can basically, yeah, to simplify, you can understand this as the tools running without optimization and the tools running with optimization. And so you see, so optimization helps. In both cases, we get a small circuit. The area is roughly half of the area of GHPC, and the randomness is roughly a quarter of that of GHPC. And latency is, of course, as desired, 1 clock cycle. So then, yeah, we also wanted to double check, let's say, the security of our Prince-S box. And so we ran it through the Silver tool. And what you see here in the table is basically the different columns are the different security notions. So probing, NI, SNI, and Piney, each time in the standard and the robust variant, so normal or glitch extended. And then in the first 2 rows, you have again the tool running without optimization. In the second row, you have the tool running with optimization, limited to the optimization steps that are allowed. Okay, and you basically see the green ticks everywhere. And then as a safety check to really say, okay, do we understand what's happening? In the third row, we let the tools run, and we allowed the tool to do this register retiming. Yeah? And then indeed you see that you get a couple of the red crosses. So this is indeed something that breaks the security, and so it's a good thing to not allow it. So then if you want to check for composability in practice, you take some round-based architecture that exists, and you plug in your S-box here, so that the circuit is just a two-share circuit, and there are 16 instances of the Prince S-box in here, because we want to keep the low latency of 1 cycle per round. And then you synthesize the same thing, and you get the area numbers here. So again, there are the two numbers for our design, for the tool running without optimization and with optimization. And well, the brief observation is that okay, it's the smallest circuit. The randomness requirement is highest, ours, but it can be optimized. So this is just, you know, not trying to reduce this. This was not the goal. Yeah. So we definitely think there's room for improvement here. Now, since we had the circuit, we also put it on an FPGA and tested it with TVLA. I'm not going to go through all of it, but basically on the left side, you have results for the RNG being switched off, so this is expected to leak. This is our test to make sure that everything is working as expected. And then on the right-hand side, you have results for the PRNG being switched on with 100 million traces, and there's no leakage shown, so we are happy, and the circuit seems to be secure. Then we wanted to understand a little bit, okay, so what's the impact of the complexity of the circuit that we're masking? So we took something bigger than a Prince S-box. We took an AES S-box. So now we have 8 input bits. We're computing 8 coordinate functions as the outputs. The approach is exactly the same, so I'm not going to show it again. So we have a first phase where we compute all the terms that we need to compute and that we can compute using only share 0 domain terms. We remask, we register, and we have a second phase in which we compute all the share domain 1 terms, and then afterwards we assemble the outputs as we need them. The result is again shown in the same way, so two results for our design. And what you see is that this way of masking is more efficient than GLM and GHPC. For AES, there is actually also an implementation in LMDPL, okay? And that one is smaller. The area number is smaller than for us. So yeah, there's still some work to be done to get there. We also put the S-box, because the S-box is too large to verify with silver, so something like this. So we just put it on FPGA and again did testing with TVLA. Same representation as before, so left-hand side, RNG is off, is expected to leak, and it leaks. And on the right-hand side, RNG is switched on, is not expected to leak, and doesn't leak. So just to summarize, I presented a novel way of doing first-order masking with latency 1 for arbitrary functions, in particular regardless of the algebraic degree of the function. It's applicable to any arbitrary Boolean function. In terms of security, in the paper, we have a security proof for first-order glitch extended Piney security. We have silver verification results for the Prince S-box, and we have practical TVLA results for a complete Prince core and for an AES S-box. Overall, what we observe with the things we implemented and tested is that we have a low area usage and a low randomness usage, and that the circuits indeed provide the security that we expected. And that's all. Thank you for your attention, and I have time for questions.
Thank you very much for the nice talk. We have some time for questions.
Hi, thank you for the talk. Because of the register retiming, is there any the circuit can be prone to clock glitch injection?
So can you say, because of register retiming,
Yeah,
whether the circuit is prone to?
to the clock glitch injection attack.
But we are not doing register retiming, right? So we're saying it is forbidden, right? It's the one optimization that we do not allow is to retime the registers.
Okay, you didn't show that register are the timing because you split the secrets in.
No, wait, so let me go back. Sorry, this is a bit slow, but we'll get there.
In the end masked.
Right, so you can see it here.
Yeah.
So I'm saying that you can allow your tools to do any kind of optimization you wish before the register and after the register, and the only thing that is not allowed is to move things across the register, because then you would start to mix the different shares together, and that's of course something you want to avoid. Okay?
Thank you.
Thanks for the great talk. On slide 21, you showed the TVLA results, and you said on the right-hand side they're not leaking.
Yes.
So for second order, I see significant values.
Yes, but of course we're claiming first order leak, so first order resistance,
Okay.
or no
Yeah.
first order leakage.
Thank you.
Second order leakage is expected and is there.
So for the full skinny, sorry, for the full skinny design, so you're doing 1 clock cycle per round, right?
The prints, you mean?
The full prints.
Yeah.
So this means that you potentially have transitions, and if I understand correctly, the composable security notion doesn't guarantee security against transition. So how did you solve that problem?
Yes, so that's so the security notion we use. So do you mean the glitch extended
Yeah.
composability? So what the circuit resists is glitches in the combinatorial logic or transitions in the registers, because the registers, right, we're remasking in every clock cycle. Remember that we have a remasking in every clock cycle?
Yeah.
So it's not possible that you overwrite, shares that are masked with the same randomness.
So you have like a full argument for that, or it's just kind of like more empirical, or did you try with some silver things that says just transition is okay?
Wait, so first let me go back, because otherwise I lose my train of thought. Where's my S-box? This is slow. Right. So for me personally, I'm happy with the TVLA results. Zeman wrote the proof, and he's here somewhere. He's there. So I suggest you have that discussion with him, because I would guess.
Thank you.
That's my honest answer.
Hi. Have you considered like higher order masks, or is it just you just targeted first order specifically?
This work is first order, and higher order extension is future work.
Okay, thanks.
Thanks.
I do have one very quick question.
Okay.
What's the main idea which you used so that your technique becomes independent of the algebraic degree? So you said like this is independent of the algebraic degree of the
Yes.
S-box. So like what's the main idea behind it?
Well, so that regardless of the function, the masked circuit always has latency 1, right? So because before, latency basically scales with the algebraic degree of the function, right? And so that's a problem, right? And so we wanted to have something that where this restriction just doesn't exist, right? So.
Okay, so let's thank the speaker again.
Thank you.
Okay, so the second talk is smooth passage with the guards, second order hardware masking of the AES with low randomness, and low latency. The authors are Barbara Giegel, Franz Klum, Stephen Mungard, Florian Mendel, Robert Pramis. And Barbara will give the talk. Can we have the slides, please?
Can you make it like full screen?
Still not in the full screen. Okay, that's fine.
Okay. Yeah, so welcome to my presentation, which is about our paper, Smooth Passage with the Guards, second-order hardware masking of the AES with low randomness and low latency. So this is joint work by my colleagues and me from Graz University of Technology, Infineon Technologies, and Intel Labs. So, okay, that also doesn't work. So this presentation is about physical side-channel attacks. We've heard a lot about that already today, so I'm going to keep it short. So essentially, you have an attacker, you have a device that stores a cryptographic key, and you want to attack that device in order to find out the key. And no, okay, it's very hard to present. I'm not having the. I don't know why it's a PDF.
Can we check this?
It's not possible. I cannot do it with the overlays. Okay, thank you so much. Yeah, so the adversary can, for example, observe the power consumption of the device while an encryption happens to find out the key. And one countermeasure we can use there is Boolean masking. The idea there is that you identify sensitive intermediate values you could use for a side-channel attack and split them up into multiple random shares. So our work is about second-order masking. So this means you would split up your sensitive value into 3 parts, such that the adversary needs to recover all 3 parts. And if only 2 parts are recovered, you cannot say anything about the sensitive intermediate values, which makes attacks very hard. So in this work, we thought about masking, and masking is actually applied on algorithmic level to your cryptographic cipher. So you identify the sensitive intermediates, split them up, and then take special care of your linear and nonlinear functions. And in practice, you won't use an algorithmic description of your masking scheme, you will use an implementation. And in our work, that's a hardware implementation. So this means you just use your AES, code it in Verilog, and put it on your FPGA. And the bad thing there is that you have things like glitches and transitions that could lead to insecure mask hardware designs. And fortunately, things like glitch-resistant masking have been proposed, like threshold implementations or domain-oriented masking that can help with that. And unfortunately, there's still a downside again. It will have a larger overhead. So masking already adds a bit of overhead to your design. And then you want to be secure against glitches, it will become even larger. And the core question in this work was, how can we decrease this overhead? How can we deal with that? And if you think about the cost of glitch-resistant masking, it will be especially manifested in area, latency, and randomness. So one thing about that is that randomness and area often go hand in hand. So if you have a large randomness consumption in your design, you need a lot of RNGs, and therefore the area of your design will be very large. And in practice, you have a trade-off between those 2 things. So you have a trade-off between latency and randomness, and if you, for example, try to optimize the latency, in the most cases, also the randomness costs will then be high. So you want low latency, you need a lot of randomness usually. On the other hand, if you want to optimize the randomness, the latency of your design will often be affected by that. And in practice, and also in our work, we targeted a design which has a good balance between those two things. So we didn't specifically optimize for latency, not for randomness, but we wanted to have a balance between those two things. And yeah, that is was the requirement and the motivation. So we wanted to have a masked AES implementation, focusing on a trade-off between those two things, protected by a second-order domain-oriented masking. And we also wanted to have a parallel implementation. So when researching for this paper, I found out that there are a lot of serial AES implementations out there which have just one SBox instance, and there are not so many that are on the other side of the scale that have like 20 SBox instances. So we wanted to target that. And everything should also be possible with an RNG that supplies 64 bits of randomness, of fresh randomness per cycle. Okay, and now I'm gonna walk you through the steps we took to achieve this and to construct this design. So our starting point was actually the AES implementation that is included in the OpenTitan project. So I think currently there's only first order masking for that. So we just implemented it such that it is second order secure, which was not that hard because DOM is a generic masking scheme. And the SBox there has a latency of 5 cycles, which is equal to the latency of 1 encryption round. And it requires 105 random bits, which means you need 20K random bits to encrypt the one plaintext block. The first step we did to optimize this was to optimize the SBox. So we focused on the SBox specifically and thought about how can we reduce the randomness while keeping the latency at the 5 cycles. And what we did there was to throw out the DOM-DEP multipliers because they are very costly and replace them by DOM-INDEP multipliers. I will give you details soon about that. And by that, you can have a design that requires 50K random bits per encryption. And if you, then we thought about what can we do even more in that direction. And we came up with a second step to apply changing of the guards on the level of the whole AES. So we thought about, can we somehow reuse the randomness that comes from the RNG in several SBoxes? And can we also use shares of unrelated state bytes instead of fresh randomness? And the answer is yes, and we managed to construct an AES implementation that can do 1 encryption at only 3K of random bits. And yeah, so now I want to give you more details specifically on the first and the second step, and I will also cover some evaluation which we did of our design. So let's start with the first step. So how did we actually optimize the AES SBox? So the starting point was the DOM AES SBox protected by second order masking. And that is based on a can-write construction, which means that you do the inversion in the finite field of 2 to the power of 8 in lower subfields because the multiplications there are easier. And domain-oriented masking proposes 2 multiplication gadgets for that purpose, the DOM-DEP and the DOM-INDEP multiplier. The DOM-DEP multiplier can multiply 2 shared variables that are statistically dependent from each other. For example, if you square a variable. While the DOM-INDEP multiplier requires that the sharing of the inputs are independent from each other. And unfortunately, there's a paper by Moos et al. That points out the flaw in the DOM-DEP multiplier starting from the order 2. And so this means that actually our starting point is the AES SBox is not really secure. So we thought about fixing that flaw, and we saw that it is actually easy to fix without any additional register stages, but you need to add more randomness, and that's actually not what we wanted. We wanted to reduce the randomness. So just to give you some numbers before, the SBox required 84 bits of fresh randomness. After our fix, it required 104. And that totals to the 20K bits for one encryption. If you want more details about what this flaw is and how we fixed it, please have a look at the paper by Morse et al. And for the fix at our paper. I'm skipping it due to time reasons. Okay, and yeah, so what are we gonna do about that? So next thing we thought is, if these DOM-DEP multipliers are so costly in the fixed version, why not just throw them out at all and try to replace them by DOM-INDEP multipliers, because they are much more cheap in terms of randomness. And the requirement for using these multipliers is that the input sharing is independent. And one thing about the input sharing of the multipliers in your SBox is that it is mostly determined by the output sharing of the previous multiplier. So if you add additional randomness to the output sharing of the previous multiplier, you could make the inputs independent. And that's exactly what we did. But we added as much fresh randomness, and in total it was still less than the fixed version of the DOM-DEP multiplier would require. So this is the resulting SBox which we constructed. So essentially the DOM-DEP multipliers in stages 1, 2, and 3 were replaced by the DOM-INDEP multipliers. Again, if you want more details here about why exactly we added randomness where and how we did that, please have a look at our paper. Yeah, and the result of that is that it needs 78 random bits. We did also an evaluation of our SBox and compared it to other works in terms of area, latency, and randomness. For instance, we compared it to the original DOM design, but also to several low latency designs. Yeah, I think the one in the middle row might be interesting because it uses less randomness than our design, has only 1 cycle latency, and is also comparable in terms of area because the same CMOS library was used, but the area is much higher than that of our work. Okay, and another part of the evaluation was actually formal verification. So we put the whole SBox design into the COCO verification tool and confirmed second-order probing security for it. Okay, and if you do that, and if you apply that optimization, you still need 50K bits of randomness for encrypting one block of plain text. This is already better than at the beginning, but we're still not there. So let's see what we can do. So let's come to the second steps. So now we want to optimize the design not only on SBox level, but on the whole architectural level. And for that, we use a concept called changing of the guards. Changing of the guards was actually introduced for something else. So actually, it was done to achieve uniformity in threshold implementations. I think in the initial paper it was a Ketchak SBox, and the output needs to be uniform. And to do so, you usually add more fresh random bits to the output. And in the changing of the guards paper, it was shown that you don't need to use fresh randomness, but you can also use an input share of another variable in your design instead of that. Okay, and in our work, we tried to apply that concept, but at a much larger scale. So we thought about how we can maybe do that concept on the whole AES level. So the thoughts we had to that was every SBox requires 78 random bits. Where do they come from? So of course, you can use them from the RNG. You can also use a guard. So in the case of our AES design, this would mean you use a share of a state byte of an unrelated SBox. I will come to the topic later what unrelated means. And we also observed that it is actually possible and quite handy to do a combination of both. So why not just use fresh randomness and combine it with a share of a state byte of another S-box, because by XORing that together, you essentially get a fresh mask out of that. And you can do that, and you can start reusing guards and fresh randomness in multiple S-boxes in your design. Of course, you need to be careful which guard you use and which S-boxes are allowed to share fresh randomness and which S-box is actually okay to take a guard from another S-box. And you need to take care about that and keep track of that. Okay, and the core of taking care of that is actually to clarify the questions, when are two computations unrelated? So when are they unrelated enough such that it is okay for them to share some randomness? And for that, we started thinking in terms of AES superboxes. So a superbox is actually a group of 4 bytes in the AES design that refers to the column E of the AES state. And there are 2 observations you can have here. First of all, the subbytes operation will process each state byte individually, but will combine the shared domains. So if you have a shared variable, the subbytes function is a nonlinear function, so it will somehow compute on all the 3 shares of your shared variable. On the other hand, mixed columns is a linear function, and this linear function will also will stay within each shared domain individually, so there is no domain crossing there. And it will combine the state bytes of 1 superbox. And if you make these 2 observations, you can come up with a concept that tells you which guards am I allowed to use at which stage in the AES box. And I just sketched it here graphically for you. So this was the concept we derived from the observation we made. So for example, it tells you in the first stage of the S-box, you can use the guards from the same superbox, then you switch to another, then you use the same again, and then you again switch to another. And then comes the mixed columns operation, and for you to not have any problems there, you need to reshare every column with fresh randomness. So in the beginning I mentioned that the RNG delivers 64 bits of fresh randomness every cycle, and in the 5th cycle of the S-box we use the 64 bits to refresh each column of the state before the mixed columns operations happen, because in mixed columns it will be combined and then you have no problems there if you refresh them. Okay, again, this was a very, very high level description about what we did. We extensively described that in the paper, so if you're interested in the details, I would also encourage you to have a look at the paper there. Yeah, but the important message here is probably if you do that, the total number of random bits can be reduced to only 3K for encrypting 1 plaintext block, which is pretty nice. For the last part of the presentation, I will briefly go over the architecture of the design and the evaluation. So, as mentioned in the beginning, the target architecture we wanted to have is a parallel architecture. So there are 20 S-boxes in your design, 4 for the key schedule, and the remaining 1 for the data path. And in total, the latency of the encryption is then, if you think about 1 S-box has a latency of 5 cycles, so you need 50 cycles to encrypt 16 bytes of plaintext, plus 1 cycle because this key schedule in our design starts 1 cycle earlier. That is because the RNG supplies 64 bits of fresh randomness per cycle, and by starting that earlier, we could balance that well without adding another RNG. Yeah, I already said that. And that is the architecture of the design, so the final architecture. So you see that we have an array of state bytes, the subbytes operation, then some module for key expansion and the RNG connected to the design. In our work, we use the Trivium RNG, but you can just use any RNG you want, essentially. Okay, then we compared our design in terms of randomness to 3 other state-of-the-art designs. The first two are, the first one is actually the original DOM design with the fixed DOM depth multiplier. So we really reduce the randomness there. The second one is a threshold implementation, which I think has also the same latency for the used S-box. It uses also much more randomness. And the third one is a design which only requires a third of the randomness we require for our design, but the latency of the S-box is, I think, a bit longer there. Okay, and a second point which I wanted to make in this presentation is what happens actually to the area of your design if you, for instance, if you do not do changing of the guards. So in the first row here, you see the area of our design and the area of the RNG. If you enable changing of the guards and you use then one instance of the trivium RNG. So you see that only 5% of the total area are used or required for the RNG. While if you turn off changing of the guards and let the RNG supply all the fresh randomness you need, then you then the area consumption of the RNG goes up to 25% of your total area consumption. And if you do not do any of the optimizations we suggested in this paper and just stick with the fixed version of the DOM depth multiplier, you need 10 RNGs, and that already accounts to a third of the whole area. Okay, we also did a security analysis of our design. So we used Coco not only for the S-box, but also used it to derive the concept I showed you with the guards, and also to verify the key schedule. So I've skipped the part with the key schedule in this presentation completely because of the time. So we also did a formal analysis of that key schedule there. And we also provide an empirical analysis. So we took the whole design and ported it to an FPGA and did physical measurements with it to show that there is no second order leakage. Okay, and that leads me to the end of my presentation. So if you have any questions, I'm happy to answer them. And please check out our paper and also the artifact which comes with the paper, because we made sure to include everything, the implementation, a test bench, the verification environment, and also the scripts you can use to measure our implementation on an FPGA board. So it's everything in the artifact. And if you want to check that out, here's the link. Thank you.
Thank you very much. We have time for a couple of questions, if there are any.
Hi, thanks for the presentation. If you go one slide back to the implementation results, I'm just curious to understand. So between the first block and the second block, what you have either you use changing of the guards or you don't. Why does that change the size of the AES? Like basically you're changing the source of the randomness, right? Either it comes from somewhere or it comes from the RNG. Why does that change the size of the AES? Do you have an idea?
Yes, so that is actually because the implementation is a proof of concept implementation, and therefore we didn't bother optimizing the way the guards are supplied to the design that much. So we just made basically a copy of the state, and in that copy we stored the guards for the design. And that's why the area here is higher if you enable changing of the guards.
Okay.
That makes sense.
Thanks.
But I guess you can get rid of that if you just try to do it or try to put in more efforts into that.
Any other question? Okay, if not, we can thank the speaker again. Okay, so the last talk is Breaking Ground, a new area record for low latency first order masked SAT3. The authors are Kangkun Zhao, Heng Zhao, Jiangxiu Liu, Bowen Yang, Bang Ping Zhu, Suying Yin, Min Zhu, Sao Jun Wei, Libo Liu. So this will be a pre-recorded talk, and the speaker will be Kankan Zhao.
Good afternoon, everyone. My name is Cankun Zhao from Tsinghua University. Welcome to my presentation on our work, Breaking Ground, a new area record for low latency first-order mask SHA-3. This project was a collaboration between Tsinghua University and Wuxi Micro Innovation Integrated Circuit Design Co. Ltd. In this work, we focused on first-order hardware masking of SHA-3, emphasizing low latency, small area, and provable security. Here's the outline of my presentation. I'll start by explaining why we need a low area, low latency mask SHA-3. Then I'll talk about the challenges in hardware masking. After that, I will review how existing works address these challenges, and finally I will introduce our approach and design solutions. Let's get started. Our work revolves around hardware masking of SHA-3. So in the first place, why does SHA-3 need hardware masking? Since this video might be uploaded to YouTube, for those who might not be familiar, SHA-3 stands for Secure Hash Algorithm 3. It's part of the Keccak family, which won the hash competition held by NIST and was standardized by NIST. At first glance, it might seem odd that a hash algorithm, unlike an encryption algorithm, does not have a key. So why does it need masking? The answer is that SHA-3 is often used to handle secrets in higher level algorithms. For example, in the post-quantum algorithm Kyber, SHA-3 is used to process secret random data and encapsulation key. In both Kyber and dilithium, SHA-3 is also used to expand secret seeds for generating pseudo-random numbers. In Keccak-based MACs, like NIST standardized KMAC, SHA-3's input also include secret keys. In all these scenarios, compromising SHA-3 to uncover these secret inputs would undermine the security of higher level algorithms. Because of this, SHA-3 becomes a target for side-channel attacks, like differential power attacks, single trace attacks, and collision-correlation attacks. Among these, differential power attack is one of the most classic side-channel attacks, which could be easily mastered by beginners with basic training. And single trace attacks means that the secret could be compromised with just a single execution of the target device. Now we know SHA-3 needs protection. But why are low area and low latency so important? First, the SHA-3 module often takes up a significant amount of area within higher level cryptographic hardware. For example, in the hardware design Kali, which is built for Kyber and dilithium, the SHA-3 module occupies 52% of the lookup tables and 36% of the flip-flops. What's worse is that this is just for the unmasked SHA-3. A masked SHA-3 consumes much more area. Currently, state-of-the-art masked SHA-3 designs requires over 4.1 times the area of the unmasked ones. Second, masked SHA-3 operations can become a speed bottleneck. For example, in dilithium's software masking, the SHA-3 operations take up 50% of the clock cycles for the entire signing process. So, creating a low area, low latency masked SHA-3 can help with these issues. but this could be a tough challenge. In hardware, there's something called glitches. Let me give you a simple example to show how glitches occur. Imagine the most basic element in hardware, an AND gate, which calculates Z as a result of X and Y. Initially, X equals 0 and Y equals 1, so Z equals 0. In the next clock cycle, X changes to 1 and Y changes to 0, so Z still equals 0. But if Y changes slightly later than X, there's a brief moment when both X and Y are 1, causing a glitch in the output Z. As you can see, glitches can occur very easily, making them hard to predict or prevent. This tiny glitch can cause big security issues. It makes the power consumption no longer tied to a single operation step, which is often the case in software. The reason is that glitches can propagate through the circuit. Even signals from far upstream can affect the power consumption of downstream operations. This creates significant challenges for designing mask hardware. To mitigate the impact of glitches on security, the most common approach is to insert registers. Registers can block glitches, but this comes at a cost. Tasks that originally took 1 clock cycle now may take 2 clock cycles after adding this one stage of registers, and may take 3 cycles with 2 stages of registers, and so on. This can result in the circuit's latency multiplying several times over. If we want to avoid glitch-induced leakage without adding too many registers and increasing latency, we need larger circuits to isolate operations that might leak. For example, to protect against first-order attacks, where the attacker can observe any single signal, the secret value must be split into at least 2 random shares, like this. However, in hardware masking, a well-known method called threshold implementation requires at least 3 shares to counteract glitches, which means using more area to split the circuit into independent parts, ensuring each part remains leakage-free. Furthermore, flash randomness is often used as a universal patch to fix leakage. Wherever there's a leakage, adding new randomness and registers usually helps. However, this flash randomness, typically sourced externally, also comes from an area consuming random number generators. So, high randomness demand can lead to significant area overhead from the random number generators. So here, security, latency, and area are at odds with one another, making hardware masking particularly challenging. So how do existing SHA-3 designs perform in terms of security, latency, and area? The CHES team proposed a TI-based design, but it fails to achieve uniformity, and is therefore not provably secure. Gross and others presented a DOM-based design, but is vulnerable to glitches. To fix the glitch issue, Gross and others added a register stage in a later version, doubling the latency. Shamirzadi and others, in their CHES 2021 design, added 2 register stages, tripling the latency. For the secure and low latency designs, the TI-based design by Bilgen and others requires over 4.1 times the area compared to the unprotected version. The design by Rebus and others, published at CHES 2018, reduces latency by half but requires over 25 times the area. The design by Zari and others, presented at CHES 2021, needs over 4.1 times the area and demands 1,600 bits of randomness per cycle. As you can see, existing designs, as they are not provably secure, suffer from multiple times the latency or require over 4.1 times the area. In our work, we present the first provably secure, no additional latency, and 3 times the area first-order mask SHA-3 hardware design. So how did we achieve this? As I mentioned earlier, CHES has many parameters, and SHA-3 only uses a subset of them. Since SHA-3 is already widely adopted and crucial, we decided to focus on protecting SHA-3 itself. Our goal was not to propose gadgets for any algorithms, but to make the SHA-3 protection fast, small, and secure. Our first step was to analyze the actual leaks within SHA-3. Not potential leaks, but the real ones. We identified, analyzed, and categorized these leaks, designing custom patches for them, while ensuring the patches were as small as possible. Finally, we provided a complete security proof and conducted several leakage tests. Now, I will briefly introduce the leaks we found and the patches we designed. Don't worry, we won't dive too deep into the details. As background, SHA-3 or CHES maintains a state array, and all operations are applied to this array. CHES parameters include multiple state array sizes, but SHA-3 only uses the 1,600-bit state array. Our first discovery was that the leakage identified by Rebus and others in CHES 2018 only occurs in smaller CHES parameters, such as the 200-bit version they used as a case study. This leakage does not exist in the 1,600-bit version used by SHA-3. However, even without that leakage, we discovered 2 other types of leakage in DOM-based SHA-3 masking, which appear at different locations and vary in difficulty to patch. The first type of leakage appears at every bit in the 1,600-bit state array. So our patch for this leakage needed to apply to all bits, significantly impacting the area. So we designed a small patch that adds just a single NOT gate to each of the state array bits. With only 1,600 NOT gates, we eliminated the first leakage. The second type of leakage appears only at bits in x coordinates 0, 1, and 3. So we only needed to handle these gates. However, we had to be careful, because glitch-induced leakage can spread throughout the circuit. You cannot just pull in a random bit from an unrelated random place as pseudo-randomness, since that could introduce new leakage. Our patch design for this type of leakage has two key points, and both of which prevent new leakage from it being introduced. First, we reused the pseudo-random numbers from COTG. COTG, changing of the guard, is a technique introduced by Professor Yun Damen to ensure uniformity and reduce the need for fresh randomness. To ensure the uniformity of one Xbox output, COTG reused an unrelated Xbox input share as a pseudo-random number to reshare this Xbox output. This reused pseudo-random number is called a guard. We used COTG in our design to ensure uniformity, and we took a step further by reusing the guard again to protect against the second type of leakage, as shown in yellow in this diagram. We placed the guard before the registers to reshare their values. This approach mitigated the leakage. However, it didn't completely eliminate it, so additional randomness was still needed. So for the state bits at x equals 0, let's look at the preceding operation of Vx. Here shows the theta operation, which XORs 11 bits together. And we pick one of the 11 bits as a pseudo-random number to reshare the register values. The benefit of this approach is that since the glitch would already propagate to the green input before the modification, so this modification doesn't introduce glitches in any additional locations. So here are all the patches we designed. We added a single NOT gate to each bit of the entire state array to eliminate the first type of leakage. For the state bits at x equals 0 and 1, we reused COTG guards without adding new gates. For the state bits at x equals 0, we reused the theta inputs to reshare the register values. These patches effectively eliminated leakage with minimal area impact. We also participated in artifact evaluation. We open sourced on GitHub our hardware design code, security analysis tools, and instructions on leakage assessments. In conclusion, the main points I'd like to leave you with is we propose the smallest secure low latency mask SHA-3, which is only 3 times the area. The previous best was 4.1 times the area. We analyzed leakage in mask SHA-3 rather than catch-up and discovered 2 new types of leakage. We provided custom patches for these 2 leakage with minimal area impact and introduced techniques like reusing guards from COTG and reusing theta inputs. Our hardware codes and related scripts are available on GitHub. I'd like to thank the anonymous reviewers for their valuable feedback, which greatly improved our paper and artifact. And special thanks to the Vermi authors for their crucial support in evaluating our design. Once again, I'm Tankun Zhao from Tsinghua University. Thank you for your attention. If you have any questions or ideas you'd like to discuss, feel free to ask now or reach out to me via email.
Okay, so the speaker is online. So if there are any questions, you may come to the mic and we can see if it works.
I think that the author probably is online and can hear me or no? I don't know.
Yes, I can hear you.
Okay. My question is about the latency. I mean, you said that you have a low latency of the Ketchak, and I guess there should be just one round of the registers or one stage of the register per round of the Ketchak, right?
Yes, yes.
Can you confirm this? Okay. Then how can you guarantee that the transitional leakages will not actually avoid any of your security properties?
Oh, thank you for your question.
I can explain it in this way. One of the papers that you cited and it showed, for example, the low latency Ketchak at arbitrary order, it has been shown later in some other works that it doesn't provide the security considering the transitional leakages. Because there is just one set of combinational circuit and one stage of the register, and the output of this register again becomes the input of the combinational circuit. Yeah, and then every clock cycle, let's say the consecutive inputs of the combinational circuit, which is masked, actually depends on itself. It means that two consecutive inputs of the combinational circuit, they are not independent of each other. And this has been, for example, checked with the ProLead tool, which takes the entire design and then can actually evaluate and find whether there is any transitional leakage. And it has been shown that that design is not secure with this respect. And now you said that you have proofs for security, and my question is whether you considered transitional leakages in the proofs.
Oh, thank you for your question. If I understand correctly, you're asking about the transition robust probing security. In my opinion, there's actual two types of transition robust probing security. They are register transitions and where transition. In our design, we proved the security of register transition. And for the wire transition, we use the ProLead for the simulation-based leakage assessment. And there's no leakage by the ProLead. And for the first register transition-based register transition probing module, we proved the security because in the glitch probing module, the attacker could observe the attacker probe the input of one register, and it propagate to a lot of registers output in the last round. And if you consider the transition-based leakage, it can add some information of the previous round of the register. So in addition to the glitch probing module, it only add one register output, the information of one register output. So this affect the leakage or the information of the attacker, this effect relatively small, and we use our custom designed Python scripts to confirm there's no this type of leakage by the transition-based probing model.
Okay, thank you.
Thank you.
Any more questions? Okay, if not, we can thank and come again. And so let's thank all the speakers of this session once again for their nice presentations. Okay, so the banquet starts at 6:30, and I think at the same venue as the lunch.